But let's move on. I'd like to introduce to you our distinguished speaker. Next speaker, Professor Alain Diebold, locally from SUNY, Polytechnic Institute. He's the Interim Dean of the College of Nanoscale Science. He's the Empire Innovation Professor of Nanoscale Science, Executive Director, Center for Nanoscale Metrology. And the main focus of Professor Diebold's research is in the area of nanoscale film structures, which requires thorough understanding of the role uniquely played by the nanoscale phenomena and the properties between semiconductors and metals. So the talk today is entitled Measurement Challenges Arising from New Semiconductor Materials and Structures for Integrated Circuits.
Thank you very much. I never like being introduced. Welcome here to SUNY Poly. We used to be mostly known as Colleges of Nanoscale Science and Engineering, which you can see on the signs in the front. That merged with SUNY IT in Utica, and so we're called SUNY Polytechnic Institute, and it's great to see a lot of people I know in the audience, including some of our industrial partners, so hopefully, us in the back of the room too, hopefully you all can get something enjoyable out of this talk. So, long ago and far away, kind of like the first Star Wars.
For recording.
All right, thank you. Long ago and far away, kind of like the first Star Wars movie introduced us to that terminology, right? A guy named Bruce Doris and I worked on looking at AFM, and at the time, AFM, that was kind of like a profilometer. It rubbed a very small tip across the surface way back then. So Bruce is, by the way, famous for making a 6 nanometer transistor at IBM like 20-some years ago or something, if I'm correct. And he's pretty well known to a lot of the IBM researchers, and he now lives in Yorktown. So Bruce has taken this kind of introductory knowledge and moved on. Back then, he was a graduate student at the University of Texas. So there is some connection to the university community here going way back. All right, so what we have here are silicon wafer incoming surface, about an angstrom, 0.3 of surface roughness, and what you see are the results of 3 different vapor phase cleaning studies. And way back then, this was very important because people were worried about silicon dioxide and silicon oxynitride gate dielectrics, and the interface between the silicon and the silicon dioxide needed to be smooth to have the electrical properties of the transistor work well. And if you're interested in some history, that article is available online. Okay. After a lot of work, the semiconductor industry came up with some concepts of what you would need to specify an incoming wafer and how you needed to specify processes in terms of surface micro roughness. In fact, if you look back at those papers, you can see some things like 2D power spectral density, which didn't seem very interesting to go into this morning, this early in the morning. So in other words, roughness isn't one number. It isn't an average roughness or RMS roughness. It is, in fact, in 2 directions, and it has spatial frequencies associated with it. But if you're to think about this in terms of something that's easy to put into a roadmap, like the International Technology Roadmap for Semiconductors that used to be around, and at the time was a very well-known instrument of exchange of information, it came up that you could specify incoming episilicon surface quality with RMS, and that was after an ammonium hydroxide, hydrogen peroxide clean for less than an angstrom. And people spent a lot of time characterizing different silicon suppliers' wafers, both epi wafers and polished silicon wafers. And they would look at a thin silicon dioxide layer and what the roughness was. They find out that it was a small bit rougher, consistently, different labs around the world, consistent. So the other thing that they found is that if they could clean the epi surface with a UV chlorine clean, they did it carefully, and they could find improved electrical properties if they did that. And so if you go on the NIST website for a conference called Frontiers of Characterization of Metrology for Nanoelectronics, or if you just click on that link, you can find Howard Huff's presentation. Howard is a he's retired now, a silicon materials expert that used to quantify the quality of incoming silicon. So people at IBM and so forth would know of his work, especially those that were around more than 10 years ago. All right, that was first connection to the semiconductor industry for AFM. Now looking a little bit more recently, CD measurements and surface shape measurement, 2D shape measurements, 3D shape measurements, sidewall roughness, and along the length of the line roughness are all important quantities. And so a particularly useful name if you're going to go Google searching on Google Scholar is John Villarubia at NIST, and here's one of his papers. And so what we're showing here is that if you have a typical shape for your AFM tip and you had a sample undercut, you might not see that undercut. But if you had a flared tip, you might be able to follow the contour of that undercut line shape. And this is a 2D line shape. Okay, so that was a nice breakthrough. People have spent a lot of time figuring out how to model the probe tip shape and deconvolute that from the image that they measure. And John Villarubia is, I'll just say, world champion in that, as are his colleagues at NIST like Andres Vladar. So here's an even more complicated paper from John and a lot of his colleagues at NIST, and like Ron Dixon and so forth. And SPIE, Advanced Lithography Conference with the Metrology, Inspection, and Process Control for microlithography, those conferences have a lot of information that perhaps the typical academic doesn't go looking in, but they have a lot of well thought out, careful information, and again, John's a good person to Google Scholar search for. And you can see here how he has worked to deconvolute what he measures in an AFM versus what the real shape of the cross-section is. And so he has software that does this kind of thing, and you can go on the NIST website and look for it. Again, John Villarubia. All right, so we see that if I can say it, in the old days, 2008 and before, you needed to measure sidewall roughness. You need to measure 3D CD, and let's compare this as we go through the talk to some of the challenges facing nanowire FET metrology. See how much more complicated it is and so forth. All right, so we just now we're going to take a look at the structures, devices, and nanoscale materials before we turn to the rest of the talk. So what are we talking about here? Well, first of all, today most of the most advanced transistors are FinFETs. So there's a fin of silicon, and here we have on the left at the top we have a cross-sectional view of a bunch of fins, and then we see a transistor made for that at the top right. All right, so that is what's in production now and so forth. What we're looking at for the future for 7 nanometer and beyond, and one of the most talked about kind of technologies are these nanowire and nanosheet FETs. And so you make those starting with a fin that has a silicon germanium, silicon germanium multilayer structure. And then through some very fancy processing, you can either make a round nanowire or a nanosheet, as you see on your far right in that lower image. Okay, so the lower on the right is IBM work, and IMEC work is there in the bottom in the center. And they have the same idea, a gate-all-around transistor. So you can get current going through the channel all the way around something instead of just on top of something. So we already start to see some of the challenges here. You got to look at the bottom of something. That's really hard to do in a non-destructive manner. All right, what about new materials? Here we have something that's near and dear to the heart of several of us in the audience here, and that is a ferroelectric material. And the interesting thing about these ferroelectrics, they have a spontaneous electric polarization, and you can switch that by the charge you put above it. So if you put that into a transistor, you can reduce its operating voltage through its negative differential capacitance, or you can put it into a non-volatile memory. And so we see drain current versus gate voltage here, and that's a nice reference in the MRS bulletin for those of you that like to read about this kind of thing. It is a very important material for the semiconductor industry right now, and it will be likely used in multiple applications. And there's even some question about whether the high K, the hafnium oxide high K that's already in your transistors maybe has a little bit of ferroelectricity in it. That's an open question that people in the literature are thinking about. All right, we'll also spend some time, since academics like to talk about the distant future too, we're going to talk about a new research material, and you already heard a really nice talk about graphene. We're going to talk about a topological insulator bismuth selenide, and I'm going to show some AFM images and some surprising things that you can find if you have a graduate student who's painstakingly careful in doing time-dependent AFM studies. All right, so let's look at the fins and what's a challenge with the fins. Well, even if you're making the fins just out of silicon, you have this process-induced challenge to the structure that you're trying to get information about called pitch walking. So you can have that happen when you use this spacer patterning process. So as you can see at the top left, as you're looking at the screen, you can see if you make a transistor type structure where that rectangle that's lighter colored is your polysilicon gate, and the spacer oxides are those red-orange curved shapes on each side of the polysilicon gate. If you get rid of the polysilicon gate and you use those spacer oxides to have a pattern to etch in the silicon below, you can get these fin structures. And because you can have two different spacings due to the spacer oxide patterning process, you get pitch walking, as you see in the bottom right as you're looking at the image there. That pitch walking, if you've ever looked at a TEM image where there's only a nanometer of pitch difference between those two, between the normal pitch that you'd expect and the pitched walked fin, it's, at least for me, visually difficult to tell that. All right, there's another aspect to all of this. If we're making silicon germanium structures, silicon germanium has a lot of biaxial stress in it. And so that biaxial stress can be relaxed when you have a fin structure. And so how much stress is in this silicon germanium structure? Well, it turns out, all right, so here we see if you pseudomorphically grow or have a good epitaxial structure, there's going to be a lot of stress in that silicon germanium layer. It's going to be compressed biaxially, and if it relaxes, that's important. And so you have a phenomenal amount, 3 gigapascals if you have 50% germanium in your silicon germanium, and that's more than these famed SOI wafers, strained silicon uninsulated wafers that used to be a hot topic in the industry. All right, so now we have that same cross-section of the fins, but the top part is silicon germanium, and we see on the other side of the overhead, you see the pitch walk structure. So let's first look at how people often characterize this, and then we'll talk about why you would want to know it if you're looking at an AFM image or trying to do some AFM characterization. So on the top, we have a single layer of silicon germanium with silicon on top. On the bottom, we have 2 of those. And you can see that in X-ray diffraction, and this is an omega 2 theta scan, even though it just says omega here, you can see that if you increase the amount of germanium, there's a change or a shift in this silicon germanium peak, which is the wider peak here in red, is more easy to see, versus the base silicon peak, which is labeled at 0 in the angular axis. If you put 2 layers in there, it gets more complicated. It's easy enough these days in the semiconductor industry to analyze this information. Nice software is available. Now let's make some fins out of that. Oh my gosh. All right. It's a good thing that there's graduate students to do all the hard work, right? Well, hard to get a laugh out of this audience. All right. So anyway, if you just have the multi-layer structure and you do a reciprocal space map, versus if you have the fins that are patterned, all of a sudden in the reciprocal space map over here, you can see in that X-ray diffraction pattern, it's a 113 for those of you that are really into X-ray diffraction patterns, you can see the satellite peaks, and there's a lot of information in those satellite peaks. And these are for 16 nanometer fins, which was an older technology. But you can get information, and what you got to worry about is that silicon germanium relaxing. Right? If it relaxes, then and you're looking at the top of these fins, you might see roughness that you didn't see before. You might see various other effects. You might see that the layers aren't what you want. They might be not, the pattern might be altered by the relaxation of stress. All right, turns out that was hard, but it's way harder now because people are doing quadruple patterning. As it's difficult to put EUV lithography in place, they've decided to do 2 spacer patterning process steps or quadruple patterning, and so you get 3 different spaces in there. So now all of your measurements, as if you're trying to do CD-AFM, this is something to consider. It's very hard to do this kind of measurement, and it turns out you can see this in X-rays, but if you're doing inline process control, this is a real problem. All right, so we've talked about having fins. We've talked about having multilayer structures. We've talked about the fact that we want to make these nanowire or nanosheet fins. So let's look at some process steps here. So the first thing you do is form the fins, and the last thing you want to do along the way is release the nanowires. So if we want to look at the surface roughness, remember we talked about in the start of the talk, we talked about the fact that it was really important to understand the surface roughness between the silicon and silicon dioxide for the electrical quality of the transistors. Now what you're worrying about are fins, these nanowires in there that are right in here that are surrounded by a lot of material. In that case, it's the spacer oxide, and you want to know what's below them and around them. That's a very big challenge for any kind of metrology technique, and it's something that is being looked at by a number of them, optical scatterometry or CD small angle X-ray scattering. And getting a probe tip in there for AFM is a challenge and something that is of significant interest. And because it takes a while of looking at this and kind of knowing more about the process flow, I labeled the fact that, for example, up here, this is a cross-sectional view through one of these fin structures here. And along the way, you do various steps until you do the nanowire release. Okay, so when you actually make one of these structures here, in this case, we're showing some structures. This is the IBM process from their 2017 VLSI Symposium presentation. You can see what a cross-section of those nanowires, or nanosheets in this case, look like, and you can see that I'm worried about the surface roughness below as well as above. Is it uniform? How does it change? Those sorts of things are all very important, and this is a really challenging process. And what you gain by having a transistor with these 3 channels in it with gate all around is you can get much more current through it. All right, here's a neat nanowire test structure. And what we're talking about is, suppose we had a AFM. Could we look in and see when you've etched away part of the silicon germanium? Can you find that? That's a challenge. That's something that we worry about, and I'd like to get some more information. Right now, the easiest way to get that information is a TEM cross-section. Slow and hard, but very accurate. And what about these nanowire fins? I showed you a couple of flavors, a nanowire and a nanosheet. But if you go in the literature, and this is a nice site, if you go in the literature, every company that's doing this has a different shape to their nanowire or nanosheet. Some have squares, some have rectangles. Some of them aren't as smooth and oval as others. It's all very different, and all of them are a big challenge, and it really depends upon what company is making this. You can find all this in the literature. All right, because the International Technology Roadmap for Semiconductors is no longer around, and now the IEEE has its own version of a technology roadmap, I found something from IMEC that talks about where transistors might go in the future, because I'm used to thinking about roadmaps. And the interesting thing that I wanted you to get out of this particular overhead is that the nanowires that we were talking about are stacked, one on top of the other. They could be vertical nanowires, or they could be done in multiple steps, like here, trying to make a bunch of transistors all together. And I don't know if you can tell, but in this particular figure right here, you're seeing nanowires that are of different materials. That's what the blue and the brown rods are meant to imply to you. So this is talking about horizontal nanowires somewhere in the 7 to 5 nanometer node, which is what I said earlier, and that kind of information is useful. And another thing this says is, at least according to this group, the nanowires won't always be horizontal. All right, we talked a little bit about the fact that we wanted to add a new material, and that new material would be the gate dielectric. The ferroelectric material would be the gate dielectric, and that's important for transistors right now, and so I showed a FinFET here, and that yellow around the fin that's underneath the gate that's shown in that light blue is where the gate dielectric goes. And so in some work that my group has done with TEL's been extremely generous here. We've been working on hafnium zirconium oxide. And here we see the multiple crystal phases. What a challenge. This is a big challenge. How do you measure the crystal phase of something that's very thin? And how do you know what's going on with those crystals? All right, so here we see the fact that if we're going to make a ferroelectric material, maybe it's not obvious to you, but these orthorhombic structures are what are believed, in particular this one is what's believed to be ferroelectric. And so the challenge is how do you tell what that crystal structure is? One way might be X-ray diffraction. Another way would to understand whether it's ferroelectric, but not necessarily know if that is the same crystal structure, is to do some electrical measurements. And so here we have a match between X-ray diffraction and some electrical measurements here for a metal insulator semiconductor structure of hafnium zirconium oxide. And the diffraction patterns here are grazing incidence X-ray diffraction patterns taken at a synchrotron, and above is the electrical data, and in particular for the charge or polarization. So polarization talks about built-in charge, but the charge versus electric field. You see hysteresis, especially in the 20 microseconds data right up there on your upper right. And you see that as you cycle it a number of times, that hysteresis pattern changes. And there is some match between the X-ray diffraction data and that electrical data. Okay, but that is a full-blown electrical test structure. All right, what's the interest here in AFM? Well, there's something called piezo force microscopy, which involves a conducting tip, and got very excited when we saw some of the papers we're going to show you in the next couple of overheads here. That includes the fact that you should be able to tell from the amplitude maps and the phase maps, and here we have, you apply a voltage with a DC and an AC component, and you can see an amplitude and phase in the surface deflection, and that should have a hysteresis loop in it in the amplitude data as shown here. And if you see that, that's a cool way to get information about the ferroelectric material. Here's another publication for silicon-doped hafnium oxide. So that's even more exciting, since the hafnium zirconium oxide is a material of great interest to the research team I was talking about. And you can see that they can map out where the ferroelectric material is here and so forth. There's even a paper that talks about using a locked-in amplifier to determine the exact direction of the polarization. And so the purpose of showing this overhead is that you can, the polarization isn't always up or down. It can be to the side or at some angle. And with a little bit of careful experimental work, as talked about in this paper here, you can determine something about the angle of the polarization. You can even determine something in the same paper about the width of the transition between if you just had up and down polarization based on the width of the probe tip. And so, of course, the bigger the probe tip, the wider the width of that transition that you're going to measure or observe. So there's some importance in understanding your probe tip if you're going to do these kinds of measurements. And as I said before, we've done a lot of work in the group here, and Steve right here is in the audience, smiling, I think. And this is the X-ray diffraction work, raising incidence X-ray diffraction, synchrotron-based. It's been done at Brookhaven as well as at the CHESS facility at Cornell. And this is how hard it is to get X-ray diffraction phase information about some of these very thin films. And here's an example of how we were able to follow from monoclinic to tetragonal for hafnium zirconium oxide with different compositions. We were able to monitor from the X-ray diffraction data what phase it is and see when it's changing between one and the other. So this kind of information can be determined, but it turns out that the ferroelectric phase is really hard to get good diffraction data on. We've been working hard on that. And there's different things in the literature that don't always match up with your own observations when you're doing these sorts of measurements. So let's quickly turn to topological insulators, in particular bismuth selenide, which is a research material, is one of these new topological insulators which have very unusual electrical properties. The momentum and spin are locked, and supposedly you can have spin-based transport across one of these materials, and small defects in the surface won't scatter that spin into a different, won't scatter an up spin into a down spin, and so forth. These are quintuple layers, so you have the yellow balls are selenium, the purple balls are bismuth, and so you have selenium, bismuth, selenium layers. These are quintuple layers. They're van der Waals bonded to each other. And so if you take a piece of Scotch tape, you can exfoliate a new clean surface. And of course, isn't PowerPoint wonderful? All right. If you buy a crystal of bismuth selenide and you do some very careful TEM sample prep, you can even see in this dark line the van der Waals spacing, and the darker white areas are the bismuth atoms. This is done on a aberration-corrected TEM. You can see the X-ray diffraction pattern here for the 0, 1, -1,5 peak. You can see the threefold symmetry that you also see in the TEM data up at the top. If you look at some of it turns out these things are used for other purposes other than topological insulators, and the literature does have a lot of information about defects, as you see this crystal defect there. It also has information about bismuth bilayers between bismuth telluride, which is a sister material or brother material, whatever you want to say, to bismuth selenide. These bismuth bilayers are important because they've been observed in X-ray diffraction and TEM studies. So we did a time-dependent oxidation study of the bismuth selenide, and if you just want to look at the oxygen 1s peak here, after 119 minutes, 2 hours, there's no oxygen peak. A little longer, there's an oxygen peak. You can see the change in the bismuth 5D and selenium 3D peaks with time. So we knew that there was oxidation going on. But curiously, when we looked at the surface in an AFM study, and so you got to give Avery some credit for being incredibly patient, he took AFM data of the surface and observed these little clumps forming with time. That was something that was very difficult to observe any other way. Interesting. So even though the oxidation doesn't show a change, the AFM showed a change in the surface. The guess was those were clumps of bismuth bilayers that had agglomerated and gone to the surface. It turns out that bismuth selenide is more air sensitive than many believe. We got some MBE grown bismuth selenide on sapphire, and the but the STM and AFM data all look the same. They have these really unusual trigonal pyramid structures, and you can see in that structure that the triangles, some are pointed up, some are pointed down, so that the crystal structure is rotated 180 degrees. It's easy enough to see that in an X-ray diffraction pattern, but the roughness of these materials, and if you're trying to use them in a device, again, there's something where a probe microscopy method gives you useful information. And so to conclude my talk, we have new materials and structures, especially structures, provide incredible challenges, and we're hoping to get more information about that, especially ferroelectric films by an AFM method called piezo force microscopy, and new materials like topological insulators. It's interesting what you can observe in an AFM measurement that you might not have seen with another measurement. And so with that, I just conclude my talk.
Great. Thank you, Alan. We can take a few questions from the audience.
Yes.
Question, when you were showing the silicon nanowire-based 7 nanometer devices, how is dopant incorporated into the nanowires? Are they implanted or diffused, or is it as grown?
So at some point, you don't need to always dope the channel. What you got to dope is the source and drain. And so that would, you would do that doping the source and drain through one of the process steps I showed. So the channel that we were, so the silicon nanowire that's been freed up, or whatever words you want to use, that particular, you're not going to find doping in that. You just want to have the gate dielectric and the metal all around it very uniform. The doping's got to be in the source and drain on each side of that channel. So these nanowire structures are amazing. You remember there was trying to remember the name of the professor at Harvard who, Charles Lieber, grew nanowires in a CVD reactor, and he grew these, concentric nanowires, and he said how we would make gate all-around transistors in the future. So after a number of years, the semiconductor industry figured out a way to make nanowires that were sitting exactly where they wanted to make a circuit, because if you just grow a nanowire in a CVD reactor, would you, hand place them in each position? So I like to think that work pointed to something that people weren't thinking about and took a long time to figure out how to do a process. This is a really hard process. I mean, as you well know, what you see in the literature is the result of lots and lots of work, and it's like what worked, right? And what didn't work, nobody knows about.
Last question.
Okay, speaking of doping of channels and lack of doping in the channel, I mean, going forward, how are we going to characterize the doping in these channels?
So,
is there AFM going to play a role in this?
So I have an answer. I got a friend who worked at IMEC, and he turned 65 and he had to retire. Wilfried Vandervorst, and he developed a method where you have a probe tip and you scan across the fin and look at where the doping is, and even has run current through transistors and done that. And SSRM, scanning spreading resistance microscopy, if I remember right. And so if you Google Scholar Wilfried Vandervorst, if you can't find him, email me and I'll send you some copies of his papers. You can see how a scan probe method was able to provide, even with the transistor working, information about where the carriers are, which is a phenomenal accomplishment. I don't know if that has been extended to an operating nanowire FET or not. I can't answer that question, but that would be the ultimate version of your question, or something like that.
Okay. All right, so with that, let's thank Alan again for a wonderful talk. And